Hello everyone. In this talk, we present scheduling weight transitions for quantization-aware training. Quantization-aware training, or QAD, simulates the quantization process during training to prevent performance degradation. It introduces quantizers and trains networks by updating latent full precision weights, which are then mapped to quantized weights. Let us look more closely at the parameter update mechanism in QAD first. Latent weights are quantized, and the gradient is computed with respect to these latent weights. Then, the latent weights are updated using a user-defined learning rate and optimizer. Importantly, a quantized weight only changes its value when the corresponding latent weight crosses a transition point, where the quantizer shifts to another discrete level. We refer to this event as a transition. In full precision training, learning rate scheduling typically reduces the learning rate progressively, enabling a course to fine update of parameters. QAD also applies a learning rate schedule to latent weights. However, the actual quantized weights, which directly influence the network outputs, are only updated indirectly through the latent weights. As a result, the learning rate controls the latent weights directly, but affects the quantized weights only indirectly. Now let us delve into the problem of learning rate scheduling in QAD. Consider a step decay learning rate. For latent weights, the degree of parameter change aligns well with the learning rate. But for quantized weights, the changes do not align as expected. This is because the update of quantized weights is determined not only by the learning rate, but also by the distribution of latent weights. A transition occurs more frequently when latent weights are close to a transition point. Therefore, simply controlling the learning rate is not sufficient to regulate the updates of quantized weights. To overcome this limitation, we propose to directly control the transition rate of quantized weights, rather than only adjusting the learning rate. By doing so, we can explicitly schedule the degree of parameter change of the quantized weights. Here is how our method works. We first define a target transition rate and introduce a momentum term that tracks the running transition rate during training. By comparing the running transition rate with the target rate, we adjust the effective update strength, which we call transition-aware learning rate. In this way, the parameter updates of latent weights are adaptively scaled to control the transition dynamics of quantized weights. Finally, let us look at the experimental results. Our method effectively regulates the update dynamics of quantized weights and consistently boosts the performance of existing optimizers. This confirms that transition rate scheduling provides a more stable and effective training process for quantized networks. Thank you for your attention. For more details, please refer to our project page.